So Quiz Tuesday, section 4 was the introduction of this idea of the derivative, f prime. F prime is the slope of f, the instantaneous rate of change of f, right? Those two things are interchangeable. Slope, when we talk about the slope of a curve, we're talking about the slope of what? Because you can't do slope of a curve, really. It's the slope of a tangent line to the curve at that point. So, okay, so we don't want to say that. That's a mouthful every time. So we want to say f prime is the slope of the tangent line to the curve f at some point. We just say it's a slope of f. But if f is a curve, okay, then at some point we can find the slope on that curve by doing a tangent line at that point and finding the slope of that line. Okay, that's what we're doing. But the problem is we only know one point on that line generally, right? The one where it's touching the curve. So how do we do that slope? And so we've been doing estimation, we've been doing rise over run. So some of the problems we did in 1.4 is here's a graph, sketch a tangent line, do the rise over run, right? If you had an equation or something you could put into your calculator, you could zoom in, zoom in. That was really 1.5, and 1.5 was about calculating those slopes. So zoom in, literally or figuratively, zoom in, pick two really close points, do a slope calculation. So we did a lot of that in 1.5, okay? Sounds like easy stuff so far, right? 1.6 then, we're getting into these connections between f and f prime. You know, if the f prime graph is positive, if the f prime graph is above the x-axis, if the f prime y values are positive, right? Always saying the same thing. Then the f graph is what? If the f prime graph is above the x-axis, if f prime is positive, what's that? Increasing. Right? If f prime is positive, I mean the slopes are positive of f, f is increasing. Okay? So that's just a connection between f prime and f. Okay? All right. So that's what 1.6 is about. So all the ramifications and questions that we can ask about that, you start to see them in the homework here. 1.7, we're then going to introduce the second derivative and see what connections that makes back to f. And look at the chart. The chart's kind of organizing all these concepts. And then that's it, okay? So we'll really pretty much get through most all of any new ideas today that are going to be on Tuesday's quiz. Monday will just be kind of finishing up and answering questions and making sure we're ready to go through the quiz. Okay? All right, homework questions. Again, this is one of those that maybe I'll just go through some stuff here, and then if you've got some other questions, we can talk about it. But it's one of those sections that's so critically important. You know, we go back to the, at the end of the year, we go back to some of the most important things we learned, the key concepts that we carried throughout the year. We would come back to this section right here is definitely one, for sure. One of the big ones, right? 1.6 and 1.7, when we learned about the chart, right? And those connections. So we've got to make sure we understand what's going on here. So we've got this picture here. Help me out. What's the first question? What's 21? What's 21 asked there? Let's open up here on page 61. So what's 21? So this is, what graph is this, by the way? This is F? Yeah. This is F, okay. Very important. What's that?
I can ask you a question.
Yeah, go ahead.
Which intervals is f prime?
Where is f prime negative? Okay. So now, the more you can do without the chart, the better. And I don't know if I don't have the chart up here. Let me pull that up here. All right. So here's similar chart that we made yesterday. Okay. So where is f prime negative? Well, we're looking when f is decreasing right here. Now, the less you need to look at the chart and the more you can just get that, the better, but it's there, right, if you need it. So All right, so where is this decreasing? Well, so then we talked about this. When it's boxed in, where are we going to put our left edge? So this graph's decreasing from where to where? -5, -2. And on any chart question, let's just clear this up right now. On any chart questions, let's do not include the intervals. Don't include, okay? I mean, there's some reasons why, and we could get into technicalities about is the graph decrease? Isn't the graph actually decreasing at -5? Can't you include -5? It's a closed interval from -5 to 5. And we can talk about why it's just not necessary. In the AP test, I think they kind of ignore it. I think on chart kind of questions, there's sometimes where it's critically important that you put the right bracket in. But on chart kind of questions, F prime increasing, decreasing, concave up, concave down, whatever. They usually just kind of ignore it, but they just say really as a general rule should be open intervals. Okay? All right, so -5, -2, and then from 2 to 5. Now, you know, is that right on 2? Yeah, we're going to assume. Now, sometimes I might do a couple different things. So I might just have you read off this graph and you assume that these are all landing at pretty nice points right here, those points of interest, okay? So typically they are. Sometimes I give you a graph where they clearly don't land on a nice point of interest. You know, maybe you're looking for this root and it lands in between here. So you just estimate what it is, okay? So you just, you know, so I'll know that when I'm grading it. If somebody's got 1.4 and somebody else has 1.3 and somebody has 1.5, okay, that's all right. You're in the ballpark. Sometimes in the directions of the problem, I'll tell you those. So I might say, okay, here's a graph F. It has roots at -3, -1, and 4.2, right? Well, then, if I give you that in the directions, I expect you to use 4.2, okay, for that one. It has local max at -2, and it has this one, and if I said it has a local max at 1.9, so then I'm telling you the local max is actually there. That's what I want you to use, okay? So, may give you a graph and don't tell you where those things are, so you may just estimate them. Or if they land right, look like they pretty much land on nice points, use that. Or I may tell you in the directions what they are. Okay, so where is F? What's the next one? F prime decreasing. F prime decreasing, we're looking where F is what? Where F prime is decreasing is what? F prime decreasing is where F is concave down. Okay? So either go to the chart or you have to think to yourself, okay, wait, slopes decreasing. How can slopes decrease? Well, they can be positive and get less positive. That'd be that. Right? Or they'd be negative and get more negative. That's concave down. Right? That's how slopes can decrease. Positive and get less positive. Negative and get more negative. That's concave down. Okay? All right. Well, that is where? Where are you going to assume that inflection point is? Did they tell you that? They didn't tell you that, did they? I think that's a fair assumption. So 0 to 5. Looks like it's concave down all the way the rest of it. Okay? All right. 22. Where is F prime positive? So now that's just the reverse intervals, right? F prime positive is when F's increasing, and where's F prime increasing would be where F is concave up. Okay? 23. Where does F prime have its max value? Where does F prime have its max value? What'd you say? Here's how I think that answer should be given, like that. Okay, instead of just 0. Okay, now would 0 be okay if I wouldn't take it off? At x equals 0 is where it happens. The inflection point, right? It's like we said yesterday. Where's a max value? Well, if you have all, and it's F prime, so we're talking about slopes, right? So if it's all positive values, it'd be the one that's the most positive. If they're all negative values, the max would be the one that's the least negative. If you have a mixture of positive and negative values, then the max value is the one that's the most positive. Well, here we have a mixture of negative slopes and positive slopes, so the max value is positive one that's the most positive, so the steepest slope, which happens at the inflection. Okay? Then it says estimate this value. So what are you going to do? Rise over run. You're going to now, it pretty much follow, the tangent line would pretty much follow that curve, wouldn't it? So give yourself a rise of 1, 1, and 1. I don't know, about 1? You say 1? I'd say that's pretty close. Looks like it's about up 1 over 1. Right? Pretty close. Right? So somewhere around 1. 24, sketch a graph of f prime. Okay? So, I'm going to do it right on top of there. Okay, so graph of f prime. So what's the slope look like right here? Pretty steep, given a number. This is where you were talking about hoping for the best, right? -5, good enough. Okay, boom. So we're down here. And then what's he getting? Negative slopes, but they're negative, but they're leveling off, aren't they? To 0 right here. 0 slope right there. 0 slope right there, right? So they're negative. So we need negative y values that are getting less negative. So it goes up like that. Okay, now we got positive slope. So now it's going to be up here, right? They're getting more positive until there. So that's going to be, now it doesn't go through that. My graph looks like it's going to go right through that point. It certainly wouldn't have to. That would be sheer coincidence. But right here, we just said that was the max value of f prime, right? We just said that in question 23. So right here is where the slope is the most positive. So that's where my y value should be the most positive, like right there. Let's make it go up there and miss that point, because that would be weird if it actually hit that point. Okay? So right up here, they're the most positive. Now they're positive slopes, but getting less positive, coming back down to here. And then they're negative and getting more negative, da, 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 da. So probably just upside down graph. Okay? All right. Let's go through this section. Okay? This time, this is a graph of what? It's G prime. Yeah. This is G prime. This is G prime. Okay? So that's a different scenario. Okay? Where is G increasing? Now, you can do this a couple different ways. If you're doing the quiz and they say, okay, this is G prime, then go in here right away. And we talked about how we really care about these points right here. See, here's what I'm talking about. We're going to have to estimate that. Well, let's call that 5.5. Okay, they didn't tell us any differently. Okay, so here's G prime. So those are going to be important points. But the maxes might be important points. Turns out the inflection points aren't really on G prime, at least for now. Okay, so where is G increasing? Well, you're going to be looking for where G prime is. Where, I heard a lot of different things there. Where is G increasing? Is when G prime is positive. G is increasing. G is increasing when G prime is positive. Which means the graph is what? When is G prime positive in a graph? In a G prime graph? When it's above the x-axis. So we care about the parts of this graph that are above the x-axis, because it does get confusing, because you're going back and forth between y values and slopes, right? One minute you're talking about where the slopes are positive. The next minute you're talking about where the y values are positive, right? Those are two different things, okay? So G is increasing when G prime is positive, means it has positive y values, so it's above the x-axis, okay? Now, here's a question for you. So, would you need to go from 0 to 1, and then from 1 to 5.5, and then from 9 to 10? By the way, you're going to have a lot of these types of questions on the quiz. If you thought this was easy, if you like this and think, man, this is not bad at all, which I think once you think of it is easy. There's a lot of points on the quiz doing this right here. So if you can get this mastered, this is going to be really good. But you can see what I mean. If you get off track on it, you can miss every single one. It's good too. Okay? So that's why it's really important to study up on this stuff. Was it necessary to shut out the 1 there? Down.
Well, that's what I was about to ask, because in the back, that's it.
They go 0 to 5.5, don't they? right? So let's talk about that. So what's the graph of G doing? If we were going to plot G right now, what would we say? Well, these are positive Y values, right? Positive and getting less positive, going down to 0. So that graph's going up, but it's level. 0 slope, flat spot, right? Because then what happens after? Keeps going up. Well, a graph like that's like x cubed. We say that that graph is continuing to increase. So when we talk about f primes increasing when f is positive, that's true, but it could be greater than or equal to 0, right? You can get a 0 slope and still have the graph be increasing. It's just at a flat spot. So yes, I would, actually, if you said this, I would accept that. But generally, when we have a flat spot, when we're talking about where is this positive, what we're really saying is where is G prime greater than or equal to 0 is what we're really saying. A little bit of a technicality, okay, but I would say a better answer would be what the back said, which would be all the way to there, okay? All right, so it just has this momentary flat spot, and then it continues on. All right, and then where is G decreasing? Well, that'd be where this is below the x-axis, so 5.5 to 9. Where does G have stationary points? I want you to write it this way. X equals 1, 5.5, and 9. Now, here's what I don't want you to write, and here's what I've seen people write, and they said, G has a stationary point. So the question was, where does G have stationary points, right? And I've seen people do this for their answer. Okay? And they're thinking of these 3 points right here, right? Why is that a wrong answer to that question? The question is, where does G have stationary points? Say it again. Thank you. James. These are points on the G prime graph. These are points on the G prime graph, right? The x coordinates are good. The y coordinates are 0 on the G prime graph, not on G. So we have no idea if these are the points on the G graph, where the stationary points are. So that is actually a wrong answer to say this, okay? And so that's why whenever the question is where, we're giving x values, just like our intervals here are x values, x coordinates. That's what we're talking about. Okay, so that's how we want the answer to look on that. Where does G have local max points? There's only one. No. 5.5. Okay. How do you get a local max? The G graph has to be going up, then down, right? That's how G has a local max. G has to go up, then down. So if G goes up, then down, what's G prime got to do? Positive to negative. That's the first derivative test. We have to have a sign. So, right here, G prime goes from positive to negative. So therefore, G is going to go from up to down. Okay? So remember I said at the beginning of this problem, I said if one of the things you might want to do, oh, here's a G prime graph. Well, anytime I have a G prime graph, I really care about where it crosses the x-axis. Well, what I also am probably going to care about is this. So a lot of times I jot that in right away. And right there, that gives me my local max stuff. Right there, it's first derivative test. This is going to go increasing and then increase some more. Well, that's flat spot. This is going to go increasing, then decreasing. That's a local max. This is going to go negative, positive. It's going to go down, up. That's a local min. Okay? So we probably just answered 29. Where's our local min? That's at x equals 9. X equals 9. Okay? So these little markings like that on a G prime graph really help me. All right. Is G concave up at 3? Well, again, it comes back to how well you know the chart. If G is concave up, G prime needs to be increasing. So we go back to the graph. Is G prime increasing there? Yes. Now, notice it says justify your answer. That's what you say. You say yes because G prime is increasing. That's why G is concave up there. Is G concave up at 6? No. Because it's, yes it is. Because G prime is decreasing. G prime decreasing means G is concave down. G prime decreasing means G is concave down. But you can see, if you can memorize the chart and just create it out of thin air, right? Once I hand out the test, you got all that stuff in front of you. It's all right there. Okay? All right. 32. The graph of G prime has a local max at 3.8 and a local min at 7.4. So that's what I was talking about earlier about giving you those values, 3.8, 7.4. What do these facts say about G? What's going on with G there? Inflection. Okay. Inflection points. Again, back to the chart. Inflection points happen on G when you change concavity. If you change concavity, it means G prime changes up to down, down to up. Okay? So if you change up to down, down to up. So what we just found out, really, local max, so this is interesting. So we use G prime to find local max and local min of G. Additionally, the local max and mins of G prime are the inflection points. Now, what about this one? Is that going to be inflection point 2 of G? They didn't talk about that one, I don't think. Is that an inflection point of G? Not one? Why was this an inflection point? Because this graph does what? Goes up, then goes down. Which means concave up, right? We just talked about that. Concave up here, and then concave down here. So that's a change of concavity, that's an inflection point. So this is decreasing, so what's G? G prime is decreasing, what's G? Concave down. And now it changes to increasing, so G is concave up. So is X equals 1 inflection point? Absolutely. Don't be fooled by the fact it hits the X. We don't care. It doesn't matter. Right? It's a flat spot. Think about a flat spot. Comes in, concave down, flat, and then come up, concave down. Flat spot is typically going to be an inflection point also. Right? It doesn't matter that it hit there. Right? Any local max or min on G prime is going to be an inflection point because it switches from up to down, increasing to decreasing, so therefore G is going to switch concavity. Suppose that G of 0 equals 0. Sketch the graph of G. Okay, so let's clear some stuff out here. I'll just graph it right up here. So we've said so many things about this graph, about the G graph. Okay, let's graph G graph. So what are we looking at now? To graph the G graph, what are we looking at? What do we care about this point right here? Okay, and it's a slope of, but we care about the Y value, right? See, back here in this problem, what do we care about right here? What were we looking at this point? Because this was F, and we were trying to graph F prime, so we wanted the slope at this point, right? The slope at this point was -5. So then we wanted to plot that. Well, now we got the reverse. This is the G prime graph, so this Y value is the slope, right? So the graph I'm looking for has a slope of 1. So I need to draw a slope of 1. Now, where do I start it? We don't know. Anyway, right? Now, remember what we said? From 0 to 5.5, this graph is doing what? The one I'm about to draw is doing what? Increasing. So I'm going to start it down here. This graph's increasing that whole time. See, now, as I went around, a lot of good stuff on your homework, but I didn't see a lot of this graph. At least not the correct one. So I'm not sure we did very good on this part. So we need to practice this a little bit. So wherever I start this, I need to start with a slope of 1. So there'd be a slope of 1 right.
Start at 0, 0.
Dallin, say that louder so
It
I
has to
can hear
start
it.
at-
'Cause
It has to start at the origin because he said G of 0 is 0.
thank you. I'm already on my 3-day weekend. We don't know where the G graph starts from the G prime graph unless they tell us, which they did. Thank you. Okay, so G of 0 is 0, so now they gave us a starting point. Okay, so now this graph has to start with a slope of 1, but what do the slopes do? They go down. What did we say we were going to have right here? Flat spot. So this is going to go to, we said this was concave down too, right? And we said it was going to be concave up. So this is going to be concave up until here, right? We said that was a what? We said that was inflection point. And now this is decreasing, so now it's concave down, but it's positive and getting less positive, so concave down means that. And we said this was a what? We said that was a local max, okay? And so now we got negative slopes and getting more negative, so down, 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 until there. And what did we say that was? Inflection point, because we had negative and getting more negative, so that's concave down. Now we got negative and getting less negative. Oh, that's concave up. So we're going to do this, and then what did we say this point was? Local minimum. And so now we got positive and getting more positive, and so it's going to go up, and there it is. Okay? So concave down to a flat spot, concave up to an inflection point, concave down to a max, concave down to an inflection point, concave up to a local minimum, and then continuing concave up and increasing it. Okay? There you go. And that is, now I don't know, again, how high this went up. I mean, I could have slope of 1. Right up here, I should have a slope of 2. So, like right here, if this y value is my slope, right here I should have a slope of 2. Does my graph look like it has a slope of 2 right here? No. So it's not a very good graph. It should have been going up steeper. This should have been going up steeper. This should probably look way higher, right? I'm not going to get real picky about that. I'm looking at shape. Right now, if you get the right shape with the concavity and stuff, we'll go with that. Later on, though, we will care more about that. We'll say we want to be a little more exact. We want to actually look at the slopes, and we'll come up with some techniques for why we might need to do that, whatever. Okay? All right. Tangent line, man. You can't go very far without having a tangent line problem. Well, you need 2 things for a tangent line. You need what? Point and the slope. Point and the slope, right? Well, we should get them all right here because we got a bunch of points, or they give us a point, and we got our slopes because that's a G prime graph right here. This guy right here is a G prime graph. That's our slopes. So what do we want? They give me the 0.34, so I put a 3 there and a 4 there. And then all I need is a slope at, I need the slope at what? It's always there, right? It's always going to be at the point where you're doing, so you say you need a point in the slope. Well, whatever this x point is, that's where you want the slope too. So at 3, what do we care about right there? We're going to look at the slope. We're going to look at the slope right here. No, because that would be what? That'd be the slope of G prime. But what's the slope of G prime? G double prime, which we're going to talk about in a minute. Okay? No, we don't want that. We want the y value right there, right? The y value right there is the slope. So we want the y value. That's 2. Stop right there. You're done. Easy problem. Look at 35. Same thing. Except now we're at 9, -1. So what's the slope at 9? 0. Just leave it. Now that would wipe that all out. It's actually a horizontal line. Y equals -1 makes sense. Y equals -1. We said that's a local min. There's a local minimum there. The slope should be a horizontal line. Y equals -1. Right? All right. Oh, look at that. Perfect. My graph is perfect right there. My tangent line was right at y equals -1. See? Look at that. All right. It's going to be a great day. 36. Could the function g be x sine x? Could that graph I drew be x sine x? No? I mean, you just plot a couple points. You could graph it on your calculator too, and you could look at it. Okay? All right. 46. So we graph this. We want to look at this graph. So I went ahead and I drew a graph of it. So this would be a situation where if they give you an equation, go to your calculator. We'll probably be allowed to use our calculators on this. I'm trying to think. But I don't know. If I'm going to give you one like this, probably. Now, to be honest, at this point, we should be able to draw this right without a calculator. Okay, it's upside down parabola, shifted up 3. Okay, we should be able to do that. Okay, that, to me, that's not asking too much anymore, right? So we talked about these transformations, all that stuff. If I give you something more like 47 or 48, yeah, then put this on your calculator and look at it, okay? So it may be a no calculator quiz just because I'm going to give you the graphs and give you simple equations that aren't going to be that difficult, So it may be no calculator, but you don't need calculators for most of us. Calculator wouldn't do you any good on these last couple of problems we've been doing. Anyway, all right. So how many roots does f prime have? So this is this f or f prime? This is f. Okay, so how many roots does f prime have? What's a root of f prime? It's when f prime is 0. So how many roots would f prime have here? 1. Right here, the slope would be 0. That's the only time the slope would be 0. Okay, so 1. Now, how many roots does this graph have? This has 2. That's the f graph. F prime would have 1 root. Where is f prime positive? F prime is positive when f is increasing. Well, that's from negative infinity to 0, right? This graph is increasing to the negative infinity to 0. Okay? Is f prime increasing at 2? F prime increasing means f is, okay, now by Monday we want to be able to shout that out in half a second, right? If f prime is increasing, f is concave up. Look at your chart, study your chart. F prime increasing means f is concave up. Is f concave up here? No. Okay, sketch a graph of f prime. So let's put a graph of f prime in here. Okay, so we'd be looking at what down here if we're going to start here? What do we look about? If we want to graph f prime, what are we looking at right here? Slope. Slope is positive and big, right? So we're going to be way up here. But the slopes are getting less positive, right? Like a slope of 20, 10, 5, 4, 3, 2, 1, 0, right? So it's coming down, 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 and it's going to have a 0 slope right there. So it's going to be coming down like so. And then what? Negative and getting negative slopes and getting more negative. Maybe something like that. Could be a line, I suppose. You could just say it's a line. Maybe it is a line. I don't know. I'm just saying it's got to come up here, come down here, come down here. Maybe it's just a line. Okay, some of you, I think, had a line when you drew it in there. Could be. Okay, could be just a line. All right. Here's 51. Okay, now a little hint about 51. This factored form. The reason that, so if I gave you this one, if I gave you this graph, okay, factored form is nice because that tells you where the roots are, right? That's why we learned all about that in Algebra 2. So this would be a parabola if I wanted to FOIL this all out, right? I mean, it'd be that, right? But it'd be nice to be in the factored form. If this is a no calculator situation, if I factor that, I'm not going to make you do it today on this one, but it'll show up later, potentially, could have to do it. So you factor it so you can see where the roots are, but I give it to you like that, that's easy. So you know where the roots are, you know it's a parabola, plot a couple points, boom, you got it. Okay? And you know where the vertex is. If you know these two roots, 1, 2, 3, 4, 5, 6 apart, so you know the vertex has got to be halfway in between, right? Of course, hopefully you remember the vertex saying negative b over 2a, find the vertex, but not going to be a big deal to have to do it. If you know a couple of points, you can always find the vertex, you know it's a parabola. Okay, simple graph like that, we should be able to draw by hand. Not a big emphasis, but it could show up. Okay, there could be one problem where I give you an equation, you better be able to sketch a graph. Could happen, okay? Not going to be a big emphasis, but it could happen. All right, so this is f prime this time. So where's f increasing when this is? This is f prime now. So f is increasing when F prime is positive. See, I heard concave up there, right? You're mixing them up. F prime's increasing, F's concave up. But when F is increasing, F prime is positive. Okay, so where this is above the x-axis, so that'd be negative infinity to negative 4, and then it would be above the x-axis from 2 to infinity. Okay? Where does F have stationary points? That's where F prime is 0. That'd be there and there. X equals 2, X equals negative 4. Where does F have local minimum? When F prime goes from local minimum, negative to positive, right there. F is going to have a local minimum at x equals 2. Local minimum at x equals 2. Okay? Because F prime is changing from negative to positive. Where is F concave down? F is concave down when F prime is decreasing. So F prime decreasing all the way until negative 1. So from negative infinity to negative 1. And if it says justify or y, you would say that's where F prime is decreasing. Okay, negative infinity to 1. Negative 1. Sketch a graph of F. Okay, so this is going to be going up, up, up. So what do I care about this point right here? This is the F prime graph. Now what do I care about that point? Its y value. I care about its y value, right? Its y value right here is a slope, because this is the F prime graph. So its y value is a slope. So I'm going to need my graph to have a slope of about 1, 2, 3 right there. So I need a graph to have a slope of 3. Do I know where to start this? Do I know where to start this? No. So I'll just start it. I'll just start it here with that. Okay, I need a slope of about 2 right there. Okay? But then the slopes get less positive, right? And what's this point going to be right here? Isn't that local max? F prime's going positive, negative. I got a local max. So this is going like that, and boom, right away here. Oh, wait, no. Yeah, my graph was going up too steep right there. Okay, so I was here, but I got to be over here a little bit. My local max has to be here at negative 4. So I got to have a local max there. So let's say we're back here. So where we started is coming up here. It's going to level off right there. So this is going to be doing this. Okay, because I got positive, positive, right? Big positive numbers here. So I got steep, steep slopes. Steep, steep slopes. So this graph's way down there. Steep, 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 steep. Coming up here to a local max right here. Now we got negative and getting more negative till there. So we got negative and getting more negative till there, right? And what point is that? When F prime has a local min or max, what do you got? Inflection point on F, because F prime is now went down to up, so F has to be concave down to concave up. So we're concave down, and we're going to switch to concave up, because now I got negative y values, but heading towards 0. So negative y values heading towards 0. We got a local min right there. And then we got positive, 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 getting more positive. There it is, right? Okay, something like that. So local max there, local min there, inflection point there. Okay. All right. Well, geez, we just about did the whole thing, didn't we? We did do the whole thing. Yeah, why even assign it? We should have just said, hey, come back tomorrow. We'll just do it for you. All right. Hopefully that's not true. Now, I saw a number of you writing as we were going. I assume you were changing, correcting. So hopefully that was valuable. Hopefully you just didn't sit there. And if you had everyone right, great. I apologize for making you sit through that all again, but that's good. You're ahead of the game. So just critically important stuff. Critically important to get that. Hopefully it advanced your knowledge of it in some little way. So let's take a look at our chart. I'm going to pull up a different version of that. So let's go to your notes and let's get the chart out here. Well, maybe I'll start here. Yeah, let's do that. All right, so F prime. This this wouldn't be bad to practice. Don't look at your notes yet. Don't look at your notes just yet. Look up here. Okay, tell me what I put in my F prime row. 0, plus, minus, up, down. Okay, that's how we start the chart every time. Okay, we just put those right in there. Now, in F prime 0, what do you got? Stationary point, local max, local min, flat spot. Right? Increase, decrease, concave up, concave down. Right? This is your first derivative test for local max and local min when you switch those columns. And this is flexion point. Switch concavity down and flexion. Okay? All right, so that's what we had yesterday. So let's bring in F double prime. Okay? So F double prime now here's the beauty of this though. What is the connections between F prime and F double prime? F prime. So it's the same as F and F prime, right? So one of the things you're going to notice today in the homework on 1.7, and we got some in 1.6, some in 1.7. In 1.7, they're going to give you an F double prime graph and ask you questions about F prime. Isn't that exactly the same thing we just got to do? That's the same as getting an F prime graph and asking about it. It's the same exact thing. So we don't have to learn any new relationships there. Matter of fact, we can put those in right now. Okay, so let's see. So now there's nothing here. There was no F prime. So just pretend this is F and F prime right now. Well, there's no F to F prime that has a 0 up here on F, right? We don't get 0 on F. Just because F is 0 doesn't tell you anything about slope, right? It just means it goes through the x-axis. Who knows what the slope would be? And there's nothing up here where F is positive, which means anything on F prime. Just because it's above the x-axis, we don't know about the slope. And just because F is negative, we don't know anything about the slope if it's below the x-axis. So there's not going to be anything here. These are just going to be blank, right? These are just going to be blank. Nothing there. You don't have to X them out or anything, but they're just nothing's going to be there. There's no connection between these on F prime and this, but there is right here, right? If F prime is increasing, what's F double prime? Positive. And if F prime is decreasing, what's negative? And then now we can see, okay, now what's missing? Okay, in other words, pretend this is our F prime row, right, down here. Well, we got our positive or negative. What are we missing? Yeah, you're missing a big one, though. The 0. Let's get that one in there. And then, yes, there's also increasing and then decreasing. So, right here, you'd have stationary point, right, local max, local min, flat spot, and then here increasing, if F double prime is increasing, F prime is concave up and concave down. Okay, so all we did there is take our F double prime row and put in those same 5 things that we had in our F prime row, and then the F, so now the F double prime row is down there, now the F prime row is there. See what I mean? So the only new thing to talk about now is what's the connection between F double prime and F. If we skip that middle row now, what does F double prime tell us about F, right? So, okay, so we learned about what does F prime tell us about F. We bring in F double prime, so now we have what does F double prime tell us about F prime. Well, that's the same thing. F double prime tells us the same thing about F prime that F prime tells us about F, so there's nothing new to learn there. So the only new thing to learn is what does F double prime tell us about F. And that is only 2 things. Well, really 3 things. That's only this section right here. This section right here is the only section where everything that in both. In other words, now what could we fill in right here? What happens if you switch these 2 columns? If F prime goes up then down, you have a
So it's
local
switch.
max, right? And if this goes down then up, you have a local min. Now a flat spot, you wouldn't switch columns, right? If you had a flat spot on F prime, it'd be going up, staying going up, or going down, stay going down, so you wouldn't have that. But we just talked about this, right? If you have an F prime here, if you have a local max or local min, its slope is 0. So you'd have an inflection point, right? Except the problem is not every time F double prime is 0 would you have a, see, what if I had this? Here's an F double prime graph right here. And what if F double prime went like that? F double prime is 0 those 2 times right there, right? If F double prime goes negative to positive, let's go back to the chart. If F double prime goes negative to positive, F double prime goes negative to positive, then F goes concave down to concave up, right? That's an inflection point. Okay? Over here, F double prime goes positive to negative. If F double prime goes positive to negative, what's F do? Concave up to concave down. That's an inflection point. But what if F double prime goes positive to positive? Is there a change in concavity? There's no inflection point. So just because F double prime is 0, you don't necessarily get an inflection point. So we're going to call that a pip. For what? Possible inflection point. Possible inflection point. Okay? Only if you change columns. Again, the only way you can have an inflection point is if the concavity changes. It's the only way. Okay, well that's going to happen if F prime is a local max or a local min, right? And at those 2 places, its slope, F double prime, is 0. But if you have a flat spot on F prime, then that's not going to cause a concavity change on F. Okay? You'll still have F double prime be 0. Okay? So F double prime being 0 is a great place to look for an inflection point. So back to what I was saying. We're trying to find what does F double prime tell us about F? Well, to be honest, look at these 3 things on F double prime and look at the 3 things up here on F. It's about concavity, isn't it? So if there's one big takeaway today about second derivative, it means concavity. Because if you're doing F double prime to F prime, okay, that's slope. And that's the same connections as F and F prime. But if we're talking F double prime to F double prime is about concavity. Second derivative is about concavity. Okay? Second derivative tells you about concavity. All right? F prime tells you about slope of F. F double prime tells you about concavity of F. All right? So, you get a bigger number for slope, it's a steeper graph. You get a bigger number for F double prime, it's a more concave graph. What does that mean? It curves more. It curves more. Okay? That's basically what you're getting. So, positive second derivative means concave up. Negative second derivative means concave down. And a 0 second derivative means maybe there's an inflection point. If F double prime switches sign, then you got to change the concavity. Just like here, if F prime changes sign, you got a local max min. So this idea of changing sign is a big one. If F prime changes sign, we got local max min. If F double prime changes signs, we got inflection point. Because we got to change the concavity. Okay, that's it. All right, let's go to page 65 real quick. Okay, we got a lot to do here in a short amount of time, but that was all really important. Okay, page 66. This is probably going to come up in some homework. I'm going to tell you, I'm going to go through a problem with you so you can see that real quick, what that means. But on page 66, down at the bottom, it says a second derivative test. And all that is this. So the first derivative test was, how do you tell if you have a local max min? Well, you check and see if the signs change. Positive to negative, local max, negative to positive, local min. Second derivative test says, okay, now we have a stationary point. We want to see if it's a local max min. Check its concavity. Think about the 3 options at a stationary point. Local min, local max, flat spot, right? Well, local min is concave up. Local max, flat spot, neither one. It's a change, right? So here's what you do. You take your stationary point and you check the second derivative. You don't have to check on either side. All you have to do is plug into the second derivative. So if you got a stationary point, look at the second derivative. If it's positive, you know the graph's concave up. That's a local min. Because a stationary point can be only one of those three things, right? Derivative 0 can only be local min, local max, or flat spot. It's got to be. So you got a stationary point, check its concavity. It's concave up. Positive second derivative, you got local min. Negative second derivative is concave down. You got local max. 0 second derivative, then probably inflection point. Okay, it's not a local max or local min. Not a big deal, but if you turn to page 68, let me just show you. I don't know if this is one of your homework questions. It is one of your homework questions. So I'll help you with it here. This is number 5, and then you can do number 6 on your own. Number 5 says, suppose that f of negative 3 is negative 1, f prime of negative 3 is 0, and f prime, double prime of negative 3 is 2. Is x equals negative 3 a local minimum? So let's talk about that. So what did they tell you when they told you f of negative 3 was negative 1? That's just a point on the f graph. That's just where it is. That's where the point is. What do they tell you when they tell you f prime of negative 3 is 0? It's a stationary point. So now we know that that point on the f graph is either a local max, a local min, or a flat spot. What do they tell us when they tell us f double prime at negative 3 is 2? They're telling me that the second derivative is positive there, so therefore the graph is concave up there. Well, I have a local min, local max, or a flat spot there. Which one of those is concave up? The local min. So therefore it is a local min, right? It's just another way of giving you information about something and you using the chart to answer that question. Okay, so we put all three of those here. Actually, the first point was irrelevant. Didn't matter, right? That was just where the point was. The second one was important because it told us we had a stationary point. So it told us it was one of those three. And then the second bit of information told us it was concave up because the second derivative was positive. And so therefore it has to be a local min. Okay, so that's how you can use this thing called the second derivative test. Doesn't come up very often, to be honest with you. We use the first derivative test way more. We look at f prime and we see it's changing positive to negative. That's a local max. We use that way more. But it can come up from time to time. All right. Let's get out our Desmos, and we got another matching activity. This time we're going to match f with f double prime. F with f double prime. Okay? Now, while you're getting that ready to go, let me show you an f double prime relationship. Now that other one is still open if you are still in that and want me to tell you if you've got some right or wrong. Somebody asked me in the other class, how do we know if we do it at home if we got them right? Well, you're right, you won't. So you may have to email me or something. Now, I'll be at parent-teacher conferences tonight, but or even over the weekend. If you want to email me, I can't promise I'll get right back to you. But if you email me, and I can look it up, and then I think somebody emailed me last night, and I sent them a screenshot of which of their cards were wrong, or whatever. So you could do that, but you could also get together with somebody else who has them right, and they can show you. So, but let me just show you right here. So what we have here is we have f on top, and we have f double prime on the bottom. So what did I just say a minute ago? The one big takeaway about f double prime is what? F double prime represents concavity. F double prime represents concavity. You really don't have to get into any increasing, decreasing discussion at all with f double prime. If you're going from f and f double prime, all you really care about is if f double prime is positive or negative, because that tells you that f is concave up or concave down. So f double prime positive means f is concave up. So when I look at this, and this is my f double prime, I'm looking negative, positive, negative. So that tells me concave up, concave down, concave up, concave down, concave up. So I need something that's going to start concave down. Well, this starts concave down. Then it switches right through here. It's concave up. Okay? Now it goes down to negative, so now it's got to be concave down. and then right here it switches to positive, switches to concave up. That's really all I'm looking for. Okay, so above the x-axis, second derivative, F's concave up. Below the x-axis, second derivative, F's concave down. Positive, negative. Okay, here's the deal. Again, the red graphs are the original. Red's the original. Blue is, you want to talk it over with somebody too as you're going along? And if you want to go back, if you get it, I want to go back to that other one we were doing. And I can show you what that was if you don't have it up. So I'm going to let you just work here now. So homework is 1.6 day 3. There's two lines right together. So there's 1.6 day 3 and then there's 1.7. Okay? And so that's the homework for Monday. And so right now you can work on this, and I'll let you know if you got good or bad pairs. You want to go back to the other one, I can put that up there, the number, if you can't get back to it, and work on that. That's not a bad one to practice either if you want to work on that for a little while. And then this homework as well. Okay? Chris, 1 bad pair. Daniel, 2 bad pairs. Dallin, 1 bad pair. Harish, 1 bad pair. Oh, also, I think when we do these decimals, I told the other class, I think you want to do sign in with Google. That helps me to track it up here, by the way. So when you go to that, it asks you to sign in. Do sign in with Google, and it just makes it a lot easier. Then you don't have to type your name in or anything. Michael, 1 bad pair. Matthew, 1 bad pair. Ryan, 1 bad pair. Sam, 4 bad pairs. Stan, 1 bad pair. Josh, 1 bad pair.
Braylon, 1 bad pair. Chris, 2. Daniel, 1. Harish, 1. Jace, 2. Jaden, 1. Josh, 1. Kobe, 1. No, Kobe, 2. Sam, no, you don't have any. Yours are all green so far. Kobe, 2 bad pairs. Michael, 2. Matthew, 2. Okay, Chris, yours are all green now. What would be the concavity of a line, by the way? 0, right? A line doesn't have concavity, so that would be 0. Yeah. So the second derivative of a line would be 0. Daniel, 2 bad pair. Harish, 2. Kobe, 1. Jaden, 1. That's all I see right now. Somebody's got 3 bad pair, but there's no name, so I don't know who that is. Haley, is that you? I don't see you on here. I've got one here that says loading. That must be you. If it is, you have 3 bad pair. Harish, 2. Jaden, 1. Daniel, 1. Kobe, 1. Sam, 2. Chloe, 1. You have 2. Okay, so let me help you on just a couple things here. So, for example, one that stands out to me right here is this line, like this V graph, right? That's what we were just talking about. So we're talking about concavity, right? So you can go either way. I would probably start looking at the blue graphs first, to be honest with you. But this one stands out to me. If that's F, what's its concavity? 0. So I'm looking for a blue graph that's where? Right on the x-axis? Way over here, right? There's 0 right there. So that V graph's got to go with that one. Now, otherwise, I would probably start looking at some blue graphs, like right here. Here's one where the blue graph is always where? Above the x-axis. So here's a blue graph that's positive, so therefore the concavity has to be concave up the whole time. So like a parabola or something that's concave up the whole time. So like that right there, right? So this is always positive. It's the only one that's that way, so it's concave up the whole time. And here's a line that's always negative, so that's got to be concave down the whole time. Okay? Pick some of our simpler blue ones. Like here's a line blue one. It's negative, then it goes to positive, right? That's what we're talking about. It's below, then it's above. So below, then above. So negative, then positive means I gotta have what? Second derivative, negative, then positive means F is concave down, concave up. So it's gotta be concave down, concave up. Kind of just like a little cubic. Kind of a cubic graph, right? Concave down, concave up. Okay? So a red graph. Right here it is. Concave down, concave up. Right? See how I'm doing that? So I would start with those simpler, like line blue functions, match those, and then get into the trickier ones. Here was the other one. Here was the one from yesterday. If you're don't still have that tab open. Say that again. Okay, let me look. So I got Haley with 2 bad pair, Braylon 1, Daniel 1, Jaden 1, Sam 2. Ivy, yours are all good. Josh, you're good. Stan, Ryan, you're good. Matthew, you're good. Kobe, you're good. Dallin, Chris, you guys are all good. Okay, so like I say, move on. You can go back and practice this other one. You can save that for later. You work on the homework, the book homework, whatever. These 2 Desmos things are not graded any more than an effort thing, kind of just like your homework right now. So that's more for your benefit to practice, because you're gonna have questions like this where not necessarily. You may have to match. I might give you a matching section and match them up, right? That could be part of what we do on the quiz next week.